Okay, good morning students. Today we are going to see the topic transition element. Into that we are going to discuss the properties of a transition element. The first property we are going to discuss about atomic size and ionic size. So generally when we move along the period, that is along the period, okay, what happened to the atomic radii? We know that along the period the atomic radii will be decreases. Along the period the atomic radii will be decreases. So when we move down the group, atomic radii will be increases. So today we are going to discuss about the atomic radii of a transition element. We know that we are going to discuss about 3D series, 4D and 5D series. So let me take first one, the 3D series element, that is 3D series. We know that 3D series element, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. The 3D transition series. If you want to discuss the atomic radii of this transition element, generally we see that along the period the ionic radii will be decreases because of the increased nuclear charge. But if you take alone, that is 3D series alone, the atomic radii is irregular. So I will give an atomic radii of 3D transition series elements first in picometer, then we will discuss what happened to the atomic radii. So if you take the atomic radii, that is given in picometer. So if I am taking the scandium, the atomic radii will be 164 picometer and the titanium will be 147 picometer, okay, and the vanadium will be 135 and the chromium will be 129 and manganese will be 131, iron will be 126, copper will be 125 and nickel also will be 125 and copper will be copper 128 and zinc will be 137. So if you take that, this is controversial point regarding on the general observation in atomic radii, because if you move to scandium to vanadium, the atomic radii is gradually that's going on decreases. But if you take after chromium, that is after vanadium, from chromium to copper, okay, it remains somewhat almost constant value. But then after copper, regarding zinc, again there will be increasing in the atomic radii. Now we are going to discuss what is the reason for a irregular decrease in atomic radii, that too in 3D series. Okay, first let me take at starting, that is from scandium to vanadium. The atomic radii is generally gradually decreases. What is the reason for that? So if you are taking the size or the atomic number scandium, if you are comparing the outer electron, so outer electron for a d block element is n minus 1 d and as well as ns electrons involved. So as well as ns electron will be involved. So here this n minus 1d will be acting as a inner shell. Okay, acting as a inner shell, and this ns electron acting as a outer shell. If you are increasing the atomic number, that is, if you are increasing the nuclear charge one by one, because we know that scandium atomic number 21, titanium 22, vanadium 23. So generally we are moving from scandium to titanium, vanadium. Gradually we are increasing the nuclear charge by +1. So where that electrons will be entered? So that the electrons will be entered only into the n-1d orbital. So if I am taking the n-1d orbital for scandium 3d1, titanium 3d2, vanadium 3d3, like it is going on. So if I am taking the d orbital alone here, suppose the d orbital, we know that there are 5 orientations. Suppose if I start with the scandium, the electron will be entered into the first orbital. Titanium, the second electron will be entered into the second. So the added electrons enter into the n-1d orbital, that is taken as the inner shell, n-1d orbital. Those added d orbital electron only will be shielded partially the nuclear charge, the increasing nuclear charge. So the added d electron partially shield the increase in nuclear charge. Partially shield the increasing nuclear charge. Okay, so partially shield the increase in nuclear charge means the effective nuclear charge that is going on increases. So effective nuclear charge increases. Okay. So when we move from one electron, second electron, the added electron enter into the d orbital, and those d electrons only partially shield the increase in nuclear charge, and because of that increase in nuclear charge, there will be what? Effective nuclear charge also increases, because the d electron will be shielded, the shielding effect will be only less. Okay, so that's why when we move from scandium to vanadium, the atomic radii will be decreases, that is gradually decreases. Okay, and next at middle. So in the middle also, now middle means we have to consider there will be pairing starting. That is, if I am taking that the D, so like this, like 1, 2, 3, 4, 5, and there will be 6, like the pairing starters. So when this pairing start means the added electron enter into the n-1d orbital. So I will clearly show you about this. You consider as a nucleus. Okay, this is considered as a nucleus. So I will show you only this will be your inner shell, that is n-1d shell, and this will be your ns shell. Suppose you consider this is the n-1d shell and this is the ns shell. Okay, so now the added electrons enter into only n-1d shell, and the electron, the ns consisting of only always 2 electron. It is depending upon the number. You may contain 1 or 2, but maximum is 2. So the ns outer electron containing how many electron means only 2, and the inner shell depending upon the element the electrons will be entered. So if you consider that as pairing starts, what's the meaning of pairing starts means number of electron increases. So if you take as the number of electrons here, suppose it is going on increases means, okay, now what happened? There will be repulsion between this n-1d electron with the ns electron. So here there is a repulsion between these 2 orbitals. Okay, and this is one repulsive force acting here. Okay, and one more thing, in addition to that, we are increasing what? nuclear charge by 1. So you have to consider that as pairing starts, there will be repulsive forces acting in between the n-1d and the ns orbital. In the same time, we are increasing the nuclear charge also. And these two forces, what are the two forces? One is the repulsive forces and increase nuclear charge. Okay, these two forces are acting in a opposite direction. Okay, acting in a what? Opposite direction, and because of that only the atomic radii of element, those element after vanadium, that is chromium to copper, remains constant. Little bit only increases, so far remains constant. So this is a situation at the middle. Suppose if you are taking at the end of the series, okay. So we are discussing about starting the number of electrons, the d electrons only little bit increases. In the middle, the d block element somewhat pairing started, so more than 1 or 2 electrons, that will be increases in the d subshell, and there your experiences the repulsive forces between the electron. But if you are taking at the end of the series, so now if you are taking at the end of the series, okay, so at the end of the series, okay, at the end of the series, now we are taking end of series. End of series means just we are containing, we are considering about a zinc. Okay, so here we are taking zinc. The outermost electronic configuration of a zinc is 3d10 4s2. Here the number of electron is only 10. Okay, so now if you are considering the nucleus of that, okay, only if I am taking this is a nucleus, if you are taking this is a n-1 d orbital, that is the inner shell, and if you are taking the outer shell, here it is in the outer shell, ns shell. So in the ns shell almost only 2 electron, but in 3d that is only 10 electrons available. Electrons available. Okay, now we have to discuss about what happened to the atomic radii. So here at the end of the series, the inner, that is n-1 d orbital contains how many electrons? 10 electrons. So here also there must be repulsive interaction between electrons. So here we have added 10 no. So the 10 means I can represent like this pairing. Okay, that is pairing. So as pairing is completely filled, okay, there are totally 10 electrons, pairing is existing fully. Now what happened, whenever the zinc containing 10 electrons in the d subshell, okay, now what happened, that the interaction between the electrons in the same orbit is more, that is we can call it as inter-electronic repulsion. Inter-electronic repulsion between the same orbital, between the same d orbital. Okay, so the repulsion is more. Okay, the repulsion is more. So inter-electronic repulsion is more comparing with the nuclear charge. That is, we can call it as effective nuclear charge. Effective nuclear charge. Okay. So now what happened? These electrons will be more repulsive force. That is inter-electronic repulsion. That is inter-electronic repulsion. That inter-electronic repulsion, okay, that should be greater than the effective nuclear charge. That should be greater than the effective nuclear charge. That is inter-electronic repulsion. Okay. Now what happened? just we are taking that the repulsion between the electron is more compared with the effective nuclear charge, because you know that the d orbital will be more, the d orbital electron will be more shielded. Okay. So now what happened? Because of that inter-electronic repulsion, increased electronic repulsion, the orbital expands. The orbital expands. Because of the inter-electronic repulsion, the orbital expands, so that the size will be increases. The size increases means the atomic radii also increases. Okay. So now just I have given a comparison only to the 3D series, that is starting, middle, at the end. Okay. So this is 3 cases we have to give an explanation. Now how can I give a comparison with 3D, 4D and 5D? Okay. So we know that 3D series, 4D series, 5D series down the group. Okay. So if I am taking the elements of 3D, 4D, 5D like that. So already 3D series elements we know. 4D series and 5D series if you are giving whole on the whole comparison. Okay. So 3D series we are starting with here. We know that scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So if I am taking 4D series, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium. And if you are taking 5D series, lanthanum, hafnium, tandium, your tungsten and rhenium, osmium, iridium, platinum, silver and gold and mercury. Okay. You compare this 3D and 4D, 5D. Let me take, already I have discussed about 3D series, no problem. There is a irregular in atomic radii. Generally, when we move down the group, what happened to the atomic radii? Down the group, atomic radii will be increases. So if I am going to compare 3D series with the 4D series, the atomic radii of the 4D series should be greater than the 3D series. This is the general trend. But the same trend, if I am going to the 4D and 5D, that is 4D transition element and 5D transition element. If you are comparing the atomic radii is almost same. That should be equal, similar atomic radii. Why? Because if you are taking zirconium and hafnium and generally niobium and tantalum, you are having similar atomic radii. You are having similar atomic radii. Why there is similar atomic radii? So if I am taking 3D, 4D is normally when we move down the group, there will be increasing in the atomic number, the nuclear charge increases, and because of that the extra orbitals will be introduced, and because of that only the size will be increases. It is clear. But if you take 4D, 5D, okay, it is almost similar atomic radii. Okay, why? The reason for this, because of the lanthanide contraction. Okay, lanthanide contraction. Now what is lanthanide contraction? This is, lanthanide contraction is nothing but imperfect shielding of a 1,4f electron by another in the same subshell. Another in the same subshell. So lanthanide contraction is nothing but, okay, that is F orbital means poor shielding. So imperfect shielding of a 1,4f electron, that is 1,4f electron by another in the same shell, same subshell. And because of that only, because due to the lanthanide contraction, the 4D transition series and 5D transition series exist almost similar atomic radii. Okay, next property we are going to discuss about ionization energy. Okay, ionization energy. So first, what is ionization energy? So it is the energy required to remove the most loosely bound electron from the isolated gaseous atom. Okay, this is the definition for ionization energy. So energy you have to supply just in order to remove the electron from the isolated gaseous atom. Now I am going to compare the ionization energy of a 3D block and 4D and 5D, that is 5D. So simply if you are giving a comparison, general D block, if I am taking comparison with S, D and P. So generally along the period, if you take ionization energy, along the period it should be increases. So along the period it should be increases, and based on this point, if you are taking the S block, D block and P block, if you are comparing S and D, ionization energy of D is greater. If you are comparing the D and P, the ionization energy of P block element is greater. This is a general explanation. And if you are going on comparing with the 3D, the ionization enthalpy only in 3D series. Okay, now what happened? Just we are taking only the 3D series. We are going to remove the electron, only which electron? Only the outer electron we are going to remove. Okay, and when we take the ionization enthalpy, gradually the ionization enthalpy, when we move from left to right along the period in 3D series, that should be gradually increases, no doubt. But if you are taking that first ionization enthalpy, that is, we can name it as IE1, that is first ionization energy or first ionization enthalpy. The first ionization enthalpy of the transition series, okay, if you are taking, that is, it is not in a regular. Not in regular, that is not in a regular format. Why? So if you are taking the 3D series, where the extra electrons will be added? The extra electron only added into the n-1 D. Okay, and that inner electrons act as a shield. Okay, inner electron act as a shield. So whenever this inner electron acting as a shield, okay, and because of that shielding effect, there will be decreasing the effective, that is the decreasing the effective nuclear charge, and there will be decreasing of the nuclear charge force, that is increasing nuclear charge on the ns electron will be decreases. So whenever if you are taking the extra electron added into the d orbital, okay, that inner electron act as a shield, and that decrease the effect of nuclear charge on ns electron. It is nothing but effective nuclear charges decreases. What is the meaning? Effective nuclear charge decreases, and because of that only we are expecting, that is the ionization enthalpy value, it is not in a regular way. It is not going on increasing in regular pattern. Okay. So next we are going to compare the ionization energy. First ionization energy, I will give you some example. The first ionization enthalpy of chromium is low. Why? Okay, just we are going to discuss the first ionization energy or enthalpy value of chromium is low. What is the reason? So if you take the chromium, the outer electronic configuration, we know that chromium is 24. The outer electronic configuration strictly we are following 3d5 4s1. 3d5 4s1. Okay. Now from that chromium 24 3d5 4s1. Okay, I am going to remove one electron. That is called the first ionization energy. So which electron I am going to remove? Only this electron I am going to remove. So chromium 3d5 4s1, into that, okay, just next I am going to remove that electron, one electron. Okay, that becomes chromium plus. Okay, what is the electronic configuration of chromium plus? Only 3d5. Only 3d5. Now let me take, this is the first ionization enthalpy. Okay, this is chromium. From that chromium, I am going to remove one electron. Okay, now why I am giving ionization energy of chromium is low. Okay, so here which electron I remove? Only the s electron. The 4s electron is incomplete. The 4s orbital is incomplete. We are having only one electron, and that electron only I am going to remove. And while I am removing that, I will get a 3d5 orbital. That is the d orbital containing how many electron? 5 electron. So just if you are taking that, this is a 5 electrons. Okay, d is containing 5 electron. Here it is not in a complete shell. So easily if you are supplying a minimum amount of energy, that electron will be coming out. So that only chromium, the first ionization energy of chromium is low. But when you compare the second, the removal of electron from the half-filled configuration is not in a very easy manner. So if you want to remove one electron, again you have to supply more amount of energy. So ionization enthalpy, that is varies. Second ionization enthalpy should be greater. Okay. So next I am going to give a comparison. Ionization energy, that is the first ionization energy of zinc is higher. Zinc is higher. Okay. Now if you are taking a zinc, the zinc will be 30 atomic number and the electronic configuration will be 3d10 and 4s2. Completely filled d subshell and completely filled s subshell. Okay. Now this is zinc. Now if I am going to remove one electron to form a first ionization enthalpy. So where I am going to remove that electron? Only the outer electron that containing s orbital, containing how many electron? Only 2, completely filled. From that completely filled orbital, I have to remove one electron. So we have to supply more amount of energy. So this becomes 3d10 4s1. So that's why the first ionization enthalpy of zinc is higher. We have to supply more amount of energy. So but generally if you are comparing the ionization energy value, usually the normal trend, that is the ionization enthalpy of a third ionization enthalpy, second ionization enthalpy should be greater compared with the first ionization energy, some exceptions. Okay. Now I am going to give a comparison. Again one more compound, you can take a copper also. So if you are taking a copper, okay, now I am taking a copper. The copper is, we know that the electronic atomic number will be 29. Okay, and if you are taking the 3d10 4s1. Okay, 3d10 4s1 because the completely filled d orbital and s. Now if I am just from that copper, I am going to remove one electron. That is first ionization energy. So where I am going to remove only this electron, so I will get 3d10. Just I am removing the 4s electron. And after that removal of one electron, we are getting the stablest electronic configuration 3d10. Okay. So Cu, here last one electron becomes what? Cu plus. Okay, Cu plus. And next, second, suppose I am going to remove one more electron. The removal is possible, but we have to supply more amount of energy to become the Cu plus 2 ions. Okay, Cu plus 2 ion. That is in the electronic configuration 3d9. So, whenever if you are comparing Cu plus and Cu plus 2, the first ionization energy, copper becomes copper, that is Cu plus, okay. The ionization energy will be low. But while you are removing one more electron from the Cu plus to form a Cu plus 2, the ionization energy involved is more. Okay. The second ionization enthalpy will be greater than the first ionization enthalpy. Here should be greater than the first ionization enthalpy. Okay, generally the ionization enthalpy, that is second ionization enthalpy, is greater than the first ionization enthalpy. Okay, and next we are going to discuss about the thermodynamic stability. That is based on the ionization energy, we can find which compound is more stable, and for that I have taken two, that is nickel plus 2 complex and platinum plus 2. Where nickel plus 2 is having a ionization energy 2490 kilojoule per mole, but in platinum the ionization energy, total ionization energy for platinum plus 2 complex 2655 kilojoule per mole. So when you are comparing this energy, that is nickel plus 2 complex is having a less energy value compared with the platinum. So nickel plus 2 complex is more stable than the platinum plus 2 complex. So this is also based on the thermodynamic stability, that is we can explain. And when we compare the 4D and 5D transition series element, usually when we move down the group, what happened? The ionization enthalpy value decreases. But here there will be exceptional case. The ionization, the too fast ionization energy of a 5D transition element is more. So normally we expected less value, but we are getting more value. And what is the reason for that? Means because of the lanthanide contraction. We know that what is lanthanide contraction means, there will be the imperfect shielding of a 1 4f electron by the another 4f electron in the same subshell. So just we have discussed that based on ionization enthalpy, we have given all the point. That is ionization comparison, first ionization, second ionization, and what happened to when we move down the group. Okay, thank you.